What if I told you the solution to Earth's energy crisis is not underground, not in the ocean, not even the wind or the sun, but buried in the dust of the moon? Right now, as you're watching this, there is a rare element sitting on the surface of the moon that could power humanity for thousands of years. It's called helium-3, and scientists believe it might be the key to clean, almost unlimited energy. No carbon emissions. No massive radioactive waste. No dependence on fossil fuels. Just pure fusion power. The same reaction that powers the sun. For decades, fusion has been called the energy of the future. But what if that future is closer than we think? What if countries are already racing back to the moon, not just for exploration, but for energy dominance? Imagine fusion reactors lighting up entire cities. Imagine deserts turning green through fusion-powered desalination. Imagine electric transportation, industries, and homes running without pollution. And now imagine this, the fuel for all of it, launched from the moon. But here's the real question. Is helium-3 truly the ultimate energy solution, or is it the most ambitious gamble in human history? In this video, we're uncovering the science, the technology, the global competition, and the bold vision behind mining the moon for helium-3. Because the next energy revolution might not happen on Earth at all. Let's begin. The future energy source, helium-3 on the moon. The world today runs on energy. Every light that turns on, every phone that charges, every train that moves, and every factory that produces goods depends on energy. For more than 100 years, most of this energy has come from fossil fuels like coal, oil, and natural gas. These fuels helped build modern civilization, but they also created serious problems. They release carbon dioxide into the air, which traps heat and causes climate change. The planet is getting warmer, glaciers are melting, sea levels are rising, and extreme weather events are becoming more common. Because of this, scientists and leaders around the world are searching for cleaner and safer energy sources for the future. Solar power and wind power are growing fast. Nuclear power also produces large amounts of electricity without carbon emissions. But many experts believe that one day, humanity may use a completely different kind of energy, something much more powerful and much cleaner. One of the most exciting ideas is helium-3, a rare form of helium that could be used in nuclear fusion reactors. And the most surprising part is this. There may be large amounts of helium-3 on the moon. Helium is a gas that most people know because it fills balloons and makes voices sound funny. But helium-3 is different from normal helium. It is a special type, or isotope, of helium. On Earth, helium-3 is extremely rare. There's only a very small amount available, and most of it is used in scientific research. But scientists believe that over billions of years, the surface of the moon has collected helium-3 from the solar wind. The solar wind is a stream of tiny particles that constantly flows out from the sun. Earth is protected from most of this solar wind by its magnetic field and atmosphere. But the moon does not have a strong magnetic field or thick atmosphere. So when the solar wind reaches the moon, some of its particles get trapped in the moon's surface dust, which is called regolith. Over a very long time, this process may have stored significant amounts of helium-3 in the lunar soil. Why is helium-3 so important? The answer lies in nuclear fusion. Nuclear fusion is the same process that powers the sun. In fusion, small atomic nuclei join together to form a larger nucleus. When this happens, a huge amount of energy is released. Fusion is different from nuclear fission, which is used in today's nuclear power plants. In fission, heavy atoms like uranium are split apart to release energy. Fission works well, but it produces radioactive waste that can remain dangerous for thousands of years. Fusion, on the other hand, has the potential to produce much less radioactive waste and to be much safer. Scientists have been trying to make fusion work on Earth for many decades. Projects like the International Thermonuclear Experimental Reactor, known as ITER, are being built to test fusion technology. ITER is located in France and involves many countries working together. Most current fusion experiments use isotopes of hydrogen, such as deuterium and tritium. But fusion between deuterium and tritium produces high-energy neutrons, which can damage reactor walls and create radioactive materials. Fusion using helium-3 could be cleaner. One possible reaction is between deuterium and helium-3. This reaction produces a lot of energy and far fewer neutrons. That means less radioactive waste and potentially safer reactors. In theory, just a small amount of helium-3 could produce an enormous amount of energy. Some estimates suggest that a few dozen tons of helium-3 could power a large country for a year. Because helium-3 is so rare on Earth, scientists started to look beyond our planet. That is when attention turned to the moon. The idea that the moon might contain useful resources is not new. During the space race in the 1960s, the United States and the Soviet Union competed to land humans on the moon. In 1969, the Apollo 11 mission successfully landed astronauts on the lunar surface. Astronauts collected rocks and soil samples and brought them back to Earth. Later analysis of these samples showed tiny amounts of helium-3 trapped in the lunar regolith. At that time, fusion technology was still far from practical use, so the discovery did not lead to immediate plans for mining the moon. But in recent years, as interest in clean energy has grown and space technology has advanced, the idea of mining helium-3 on the moon has become more serious. Countries like the United States, China, and others have announced plans to return to the moon. NASA is leading the Artemis program, which aims to send astronauts back to the moon and build a long-term presence there. China has also launched several lunar missions and has spoken openly about the potential of helium-3 as a future energy source. The moon is only about 384,400 kilometers away from Earth. In space terms, that is very close. It takes only a few days for a spacecraft to travel there. Compared to other planets, the moon is the most realistic place to start space mining. But even so, mining helium-3 on the moon would be extremely challenging. The concentration of helium-3 in lunar soil is very low. To collect useful amounts, huge quantities of regolith would need to be processed. This would require advanced robots, powerful machines, and a lot of energy on the moon itself. There would also need to be systems to transport the helium-3 back to Earth safely and economically. Even if we could bring helium-3 to Earth, we would still need working fusion reactors that can use it efficiently. Right now, no commercial fusion power plant exists anywhere in the world. Fusion remains one of the greatest scientific and engineering challenges of our time. So the idea of helium-3 from the moon depends on two major breakthroughs: practical fusion energy and large-scale lunar mining. Despite these challenges, the idea continues to inspire scientists, engineers, and policymakers. It represents a vision of the future where humanity expands beyond Earth, uses the resources of space, and solves its energy problems in a clean and powerful way. It combines space exploration, advanced physics, global cooperation, and the dream of sustainable energy. For some people, helium-3 on the moon sounds like science fiction. But many technologies we use today once sounded like science fiction too. Satellites, smartphones, reusable rockets, and even the moon landing itself were once considered impossible. Today, private companies like SpaceX have reduced the cost of launching rockets. Reusable launch systems are becoming more common. As space travel becomes more affordable, the idea of building bases on the moon becomes more realistic. A lunar base could serve many purposes. It could support scientific research, test new technologies, and act as a stepping stone for missions to Mars. It could also become a center for resource extraction, including water ice and possibly helium-3. Water on the moon can be split into hydrogen and oxygen, which can be used as rocket fuel. This means the moon could become a refueling station in space, reducing the need to launch everything from Earth. In this larger vision, helium-3 is not just an energy source. It is part of a bigger story about humanity becoming a multi-planetary species. It is about learning to live and work beyond our home planet. It is about using knowledge and technology to solve global problems. Understanding fusion and why helium-3 matters. To understand why helium-3 on the moon is such an exciting idea, we must first understand nuclear fusion in a simple way. Fusion is the process that powers the sun and all the stars in the universe. The sun shines because deep inside it, under extremely high temperature and pressure, tiny atoms are forced to join together. When they join, they release an enormous amount of energy. This energy travels through space as light and heat, and it is the reason life exists on Earth. Without fusion in the sun, our planet would be cold and dark. At the center of the sun, hydrogen atoms move very fast because the temperature is millions of degrees. When these hydrogen atoms crash into each other with enough force, they combine to form helium. This joining of small atoms into a bigger atom is called nuclear fusion. During this process, a small amount of mass is converted into energy. This idea was explained by Albert Einstein in his famous equation E=mc². The equation shows that even a tiny amount of mass can be turned into a huge amount of energy. Scientists have been trying for decades to recreate this process on Earth. If we can control fusion safely and continuously, we could produce almost unlimited clean energy. The fuel for fusion is abundant. Deuterium, one type of hydrogen used in fusion, can be found in seawater. Tritium can be produced from lithium. If fusion becomes practical, the fuel supply could last for millions of years. But making fusion work on Earth is extremely difficult. The main challenge is temperature. To force atoms to fuse, they must be heated to very high temperatures, even hotter than the center of the sun. At such temperatures, matter becomes plasma, a special state where electrons are separated from nuclei. This plasma must be contained and controlled without touching any solid surface, because it would melt anything it touches. Scientists use powerful magnetic fields to hold and control this hot plasma. One of the most advanced fusion designs is called a tokamak. A tokamak is a large donut-shaped machine that uses magnets to confine plasma. The international project called ITER, located in France, is building the largest tokamak ever made. Many countries are involved in this project, including members of the European Union, the United States, China, India, Japan, Russia, and South Korea. The goal of ITER is to demonstrate that fusion can produce more energy than it consumes. If successful, it will be a major step toward commercial fusion power plants. Most fusion experiments today use a reaction between deuterium and tritium. This reaction is currently the easiest to achieve in a laboratory. When deuterium and tritium fuse, they produce helium and a high-energy neutron, along with a large amount of energy. However, those high-energy neutrons create problems. They can damage the walls of the reactor over time, making the materials radioactive and requiring regular replacement. This increases cost and complexity. Now, this is where helium-3 becomes interesting. Helium-3 can be used in a different type of fusion reaction. One possible reaction is between deuterium and helium-3. When these two fuse, they produce helium and a proton instead of a neutron. This reaction releases energy, but produces far fewer neutrons. That means less radioactive waste and less damage to the reactor structure. In simple words, helium-3 fusion could be cleaner and safer compared to deuterium-tritium fusion. There is also another possible reaction between two helium-3 atoms, but this requires even higher temperatures and is currently much more difficult to achieve. Even so, the main advantage of helium-3 is that it reduces the neutron problem. With fewer neutrons, the reactor materials would last longer and the waste would be much less dangerous. This is one reason why some scientists call helium-3 the ideal fusion fuel. However, there's a major problem. Helium-3 is extremely rare on Earth. Small amounts are produced by the decay of tritium, and some can be found in natural gas deposits, but the total amount available is tiny. It is estimated that all the helium-3 on Earth would only be enough for limited research use. it is not nearly enough to power the world. That is why researchers began looking at the moon. Over billions of years, the solar wind has been hitting the lunar surface. The solar wind contains small amounts of helium-3. Because the moon has no thick atmosphere and no strong magnetic field like Earth, these particles are not blocked. Instead, they become embedded in the top layers of lunar soil. Scientists studying samples brought back by the Apollo missions found traces of helium-3 in the regolith. Estimates suggest that the moon may contain up to 1 million tons of helium-3, although the exact amount is still uncertain. Even if only a small fraction of this is economically recoverable, it could represent a huge energy resource. Some studies suggest that 1 ton of helium-3, if used in a fusion reactor, could produce as much energy as millions of tons of coal. This sounds almost unbelievable, but it is based on the incredible energy density of nuclear reactions. Compared to chemical reactions like burning coal or oil, nuclear reactions release millions of times more energy per unit of mass. To imagine this more clearly, think of a small truck carrying a few tons of helium-3. In theory, that small truck could carry enough fuel to power a large city for a year if fusion technology is fully developed. The environmental benefits could also be significant. Fusion does not produce carbon dioxide. It does not produce long-lived radioactive waste like traditional nuclear fission. There is no risk of a runaway chain reaction like in a fission reactor meltdown. If something goes wrong in a fusion reactor, the reaction simply stops. This makes fusion inherently safer. However, we must be realistic. Helium-3 fusion is even more difficult to achieve than deuterium-tritium fusion. It requires higher temperatures and better plasma control. So before we even think about mining helium-3 on the moon, scientists must first prove that helium-3 fusion is practical and economically viable. Today, private companies as well as government research centers are racing to achieve fusion energy. Some companies claim they may produce commercial fusion power within the next few decades. If that happens, the demand for fusion fuel will increase. At that point, the question of fuel supply will become more important. If deuterium-tritium fusion becomes common, we may not need helium-3 at first. But if helium-3 fusion becomes possible and proves to be superior, then the moon could become a strategic energy resource. In this way, helium-3 is connected not only to science, but also to economics, politics, and the future balance of power in the world. Energy has always shaped history. Countries with large energy resources often gain economic and political influence. In the past, oil-rich regions became very important. In the future, could lunar resources become just as important? The idea may sound futuristic, but serious discussions are already happening in scientific and policy communities. In the next part, we will explore how helium-3 could actually be mined from a moon, what kind of machines would be needed, how people might live and work on a lunar base, and what challenges we would face in turning this bold idea into reality. How helium-3 could be mined on the moon, and the challenges ahead if humanity decides to use helium-3 from the moon as a future energy source. The next big question is simple but powerful. How do we actually get it? The idea of mining on the moon may sound like something from a science fiction movie, but scientists and engineers are already studying it seriously. To understand the challenge, we must first understand where helium-3 is located. Helium-3 is not found in large underground pockets like oil or natural gas on Earth. Instead, it is spread in tiny amounts across the surface layer of the moon, mixed into the fine dust and broken rock called regolith. This regolith covers most of the lunar surface and was created by billions of years of meteor impacts. Over time, particles from the solar wind, including helium-3, became trapped in this upper layer. The concentration of helium-3 in lunar soil is very low. On average, there may be only a few parts per billion. That means to collect a meaningful amount, enormous quantities of soil would need to be processed. For example, to collect 1 ton of helium-3 millions of tons of regolith might need to be heated and treated. This tells us immediately that mining helium-3 would not be easy or cheap. It would require large-scale industrial operations on the moon. The first step would be establishing a permanent or semi-permanent base on the moon. Programs like NASA's Artemis program are already planning to send astronauts back to the lunar surface. The Artemis missions aim to build infrastructure such as habitats, power systems, and communication networks. These would be necessary foundations for any future mining activity. Other countries are also active. China's lunar exploration program has successfully landed robotic missions on the moon and returned samples to Earth. As space technology becomes more advanced and more affordable, the idea of building a working lunar base becomes more realistic. At a lunar mining site, large robotic machines would likely do most of the work. Because the moon has no atmosphere and very extreme temperatures, machines must be designed to survive harsh conditions. During the lunar day, surface temperatures can rise above 100 degrees Celsius. During the lunar night, temperatures can fall below minus 150 degrees Celsius. Each lunar day and night cycle lasts about 14 Earth days. So equipment must handle long periods of heat and cold. Mining helium-3 would likely involve scooping up regolith and heating it to high temperatures, possibly around 600 to 900 degrees Celsius. When heated, the gases trapped in the soil, including helium-3, would be released. These gases could then be collected, separated, and stored. The remaining soil might be returned to the surface. The heating process would require a lot of energy. Therefore, a lunar mining base would need a strong and reliable power source. Solar power is one option, especially in regions near the lunar poles where sunlight may be available for long periods. Another option could be small nuclear reactors placed on the moon to provide constant electricity. Some scientists suggest that the lunar poles may be the best place for a base. Observations have shown that craters near the poles contain water ice. Water is extremely valuable in space. It can be used for drinking, for growing plants, and most importantly, it can be split into hydrogen and oxygen to create rocket fuel. If a base near the poles could produce its own fuel, it would reduce the need to launch everything from Earth. This would lower costs and make large-scale mining more practical. After helium-3 is collected and purified, the next challenge would be transporting it back to Earth. Rockets would need to launch from the moon's surface in a lunar orbit, then transfer to Earth orbit, and finally deliver the cargo safely. The moon's gravity is much weaker than Earth's, so launching from the moon requires less energy than launching from Earth. This is an advantage. However, space transport is still expensive and technically complex. To make helium-3 mining economically viable, the total cost of extraction and transport must be lower than the value of the energy it can produce on Earth. This calculation depends heavily on whether fusion reactors using helium-3 become efficient and commercially successful. If fusion remains too expensive or difficult, then mining helium-3 would not make financial sense. In addition to technical challenges, there are legal and political questions. Who owns the resources of the moon? The Outer Space Treaty of 1967, signed by many countries, states that no nation can claim ownership of the moon or other celestial bodies. Space is considered the province of all humankind. However, the treaty does not clearly define how resources can be used. In recent years, some countries have passed national laws allowing private companies to extract and own space resources. This has created debate about fairness and international cooperation. If helium-3 becomes valuable, competition between countries or companies could increase. Some experts believe that international agreements will be necessary to prevent conflict and to ensure that lunar resources are shared in a peaceful way. Just as oil shaped global politics in the 20th century, space resources could influence the 21st century. There are also environmental concerns. Although the moon has no life and no ecosystem like Earth, large-scale mining could still change its surface. Some scientists argue that we should protect certain areas of the moon for scientific research or cultural heritage, such as the historic landing sites of the Apollo missions. Balancing economic activity with preservation will be an important discussion. Despite all these challenges, many researchers remain optimistic. Technology is advancing quickly. Reusable rockets developed by companies like SpaceX have already reduced launch costs significantly. Robotics, artificial intelligence, and autonomous systems are improving every year. What seems extremely difficult today may become normal in a few decades. Throughout history, humanity has expanded into new frontiers. We crossed oceans, explored continents, drilled deep underground, and built cities in deserts. Each step required courage, investment, and innovation. The moon could be the next frontier. Helium-3 represents more than just a fuel. It symbolizes a future where humanity uses space resources to solve problems on Earth. It connects clean energy with space exploration. It challenges us to think beyond our planet and to imagine a civilization that is not limited to one world. But we must also stay realistic. Fusion energy has not yet been achieved at a commercial level. Lunar mining has never been done. The cost would be enormous, and the risks are high. The dream of helium-3 from the moon depends on many breakthroughs happening together. In the next part, we will explore the economic impact, the global competition, and the long-term vision of a world powered by fusion energy from space. We will ask whether this dream is likely to become reality in our lifetime, or whether it remains a vision for future generations. Economics, global competition, and the long-term vision of a fusion-powered world. If helium-3 from the moon ever becomes a real energy source, it will not only change science and technology, it will change the global economy and the balance of power between nations. Energy has always shaped human history. In the past, countries with large coal reserves became industrial powers. Later, oil-rich nations gained economic strength and political influence. Today, access to clean energy technologies such as solar panels, batteries, and rare earth minerals plays an important role in global competition. If fusion energy becomes practical and helium-3 becomes a valuable fuel, the moon itself could become one of the most strategic locations in human history. Let's first consider the economic side. Building fusion reactors on Earth is already extremely expensive. Projects like ITER require billions of dollars and decades of work. Developing helium-3 fusion would require even more research because it needs higher temperatures and more advanced plasma control systems than current deuterium-tritium designs. At the same time, establishing mining operations on the moon would require heavy investment in rockets, lunar landers, habitats, robots, power systems, and transport vehicles. The total cost could reach hundreds of billions of dollars before the first kilogram of helium-3 is ever sold. For this reason, helium-3 mining would likely begin only if fusion energy proves successful and profitable. Investors and governments would need strong evidence that helium-3 fusion reactors can operate reliably and produce electricity at a competitive price. Energy markets are very sensitive to cost. Today, solar and wind power have become much cheaper than they were 20 years ago. Battery storage is also improving. Any new energy source must compete with these technologies. If fusion energy, including helium-3 fusion, can provide steady, large-scale electricity without carbon emissions and with minimal waste, it could become very attractive, especially for countries that need stable power for large cities and industries. Now let us think about global competition. Several major space powers are already planning long-term lunar missions. The United States, through NASA and its Artemis program, aims to return astronauts to the moon and build a sustainable presence. China has its own lunar exploration plans and has successfully completed robotic sample return missions. Russia has also expressed interest in lunar cooperation. Private companies are becoming more involved as well. If helium-3 becomes valuable, countries with advanced space technology will have an advantage. This could lead to a new kind of space race, not just for national pride, but for economic opportunity. However, this competition could also encourage cooperation. Large space projects are expensive, and sharing costs can make them more realistic. The International Space Station is an example of countries working together in orbit. A similar model could be used for lunar bases and resource extraction. International agreements may be necessary to define how helium-3 and other lunar resources are shared. The Outer Space Treaty states that outer space belongs to all humanity, but does not give detailed rules for commercial mining. New agreements could help prevent conflict and ensure peaceful use of the moon. Beyond economics and politics, helium-3 from the moon represents a powerful long-term vision. Imagine a future where cities are powered by clean fusion energy. Power plants produce massive amounts of electricity without smoke, without greenhouse gases, and without long-lived radioactive waste. Electricity becomes cheaper and more abundant. Desalination plants provide fresh water to dry regions. Electric vehicles charge quickly and travel long distances. Heavy industries operate without polluting the atmosphere. Developing countries gain access to reliable power, helping reduce poverty and improve living standards. At the same time, humanity expands its presence in space. Permanent bases on the moon support mining, scientific research, and even tourism. The moon becomes a training ground for missions to Mars and beyond. Space transportation becomes more common and less expensive. Children grow up seeing space not as a distant dream, but as a normal part of human activity. In this vision, helium-3 is more than fuel. It is a bridge between Earth and space. It connects our need for clean energy with our desire to explore. It shows how solving one problem can open the door to many new possibilities. But we must also ask an important question. Is this likely to happen in our lifetime? The honest answer is uncertain. Fusion energy has been called the energy of the future for many decades. Some scientists believe commercial fusion could become available within the next 30 years. Others believe it may take longer. Even if deuterium-tritium fusion becomes common first, helium-3 fusion may remain a longer-term goal because of its technical difficulty. Mining helium-3 on the moon would probably happen only after fusion power plants are already operating on Earth. It would be a second step, not the first. So helium-3 from the moon may not solve our immediate energy challenges. In the near future, solar, wind, battery storage, and possibly advanced fission reactors will likely continue to grow. These technologies are already available and improving. Fusion, including helium-3 fusion, may become part of the energy mix later in the century. Still, long-term thinking is important. Great achievements often require decades of preparation. When humans first looked at the moon, it seemed unreachable. Yet in 1969, astronauts walked on its surface. At that time, computers were far less powerful than the smartphones we use today. Progress can happen faster than we expect when science, investment, and determination come together. In conclusion, helium-3 on the moon represents one of the most ambitious energy ideas ever imagined. It combines advanced nuclear physics, large-scale space engineering, global politics, and economic strategy. It faces serious challenges, both technical and financial. Yet it also offers a powerful vision of a cleaner and more advanced civilization. Whether it becomes reality or remains a bold dream will depend on the choices we make today in research, cooperation, and exploration. The story of helium-3 is not only about the moon. It is about humanity's ability to think big, to plan for the long term, and to reach beyond limits in search of a better future. A future written in lunar dust. The deeper reality behind the dream. Now, let us step back and imagine the bigger picture, not just as scientists or engineers, but as human beings thinking about the future of our civilization. For thousands of years, humanity has looked up at the moon with curiosity and wonder. Ancient cultures created stories about it. Poets wrote about it. Sailors used it to guide their journeys across dark oceans. Then in the 20th century, humans finally reached it through the Apollo program led by NASA, and the first footprints were left on its silent surface. Those footprints are still there today, untouched because there is no wind on the moon to erase them. Now we're asking a new question. Could the same moon that inspired myths and dreams also power our cities in the future? The idea of helium-3 on the moon forces us to think on a scale much larger than daily politics or short-term problems. It pushes us to think in decades and even centuries. If fusion energy becomes practical, it could change everything about how we live. Energy is the foundation of modern life. Without it, hospitals cannot function, communication systems fail, factories stop, and transportation slows down. As the global population grows and developing nations seek higher living standards, energy demand continues to rise. At the same time, climate change reminds us that we cannot continue burning fossil fuels forever. We need cleaner solutions. Renewable energy like solar and wind will play a major role. They are already transforming electricity production, but renewables depend on weather conditions. The sun does not shine at night, and the wind does not always blow. Battery technology helps, but storing massive amounts of energy for entire cities remains expensive and technically challenging. Fusion energy, if mastered, would provide steady, large-scale power at any time of day, in any season. Helium-3 fusion, in particular, promises a cleaner reaction with fewer radioactive byproducts. That is why it captures so much attention. However, the journey from idea to reality is long and complex. First, scientists must prove that helium-3 fusion can work efficiently in a controlled reactor. Current research focuses mainly on deuterium-tritium fusion because it requires slightly lower temperatures. Helium-3 reactions demand even higher heat and stronger magnetic confinement. This means new materials, better superconducting magnets, improved plasma control systems, and advanced reactor designs must be developed. Private fusion companies are experimenting with different approaches, including compact reactors and alternative confinement methods. Governments continue to invest billions into large research facilities. Progress is steady, but it requires patience. Second, even if fusion becomes commercially viable, mining helium-3 on the moon must make economic sense. The concentration of helium-3 in lunar soil is low. Massive robotic operations would need to dig, transport, heat, and process regolith continuously. Infrastructure would have to survive radiation from space, micrometeorite impacts, and extreme temperature changes. Astronauts or technicians might live in protected habitats, possibly underground or shielded by lunar soil to block cosmic rays. Artificial intelligence and automation would likely control most daily operations. Over time, a lunar industrial zone could develop, powered by solar arrays spread across the surface. Rockets carrying refined helium-3 would launch toward Earth on regular schedules. This scenario may sound distant, but remember how quickly technology has evolved in recent decades. Reusable rockets dramatically reduced launch costs. Satellites now provide global internet coverage. Robotics can perform delicate surgeries and explore the deepest parts of our oceans. Human innovation moves forward step by step. There's also a philosophical side to this story. For the first time in history, humanity has the potential to use resources beyond Earth to solve problems on Earth. In the past, when resources became scarce in one region, people moved to another part of the planet. Now, the next frontier is space. The moon is close enough to reach within days, yet far enough to challenge our engineering skills. Mining helium-3 would represent a shift in how we see our place in the universe. We would no longer be limited to one world. At the same time, we must think carefully about responsibility. Space should not become another area of uncontrolled competition or conflict. International cooperation will be essential. Clear rules must guide resource use. Scientific research sites and historic landing areas should be protected. The benefits of fusion energy should ideally be shared globally, not concentrated in a few powerful nations. If managed wisely, helium-3 could become a symbol of cooperation rather than rivalry. If managed poorly, it could increase tensions. The future depends not only on technology, but also on human choices. It is also possible that alternative energy breakthroughs will make helium-3 less necessary. Advanced battery systems, improved renewable grids, or new forms of fission reactors could provide sufficient clean energy without lunar mining. Science is unpredictable. Sometimes the solution we expect turns out to be different from the one that succeeds. But even if helium-3 mining never becomes large-scale reality, the research itself drives innovation. Developing fusion reactors improves materials science, superconductivity, and plasma physics. Building lunar missions advances robotics, life support systems, and space transportation. These technologies can benefit life on Earth in many ways. So in the end, helium-3 on the moon represents both a practical possibility and a powerful symbol. It symbolizes hope for clean energy. It symbolizes the courage to explore. It symbolizes long-term thinking in a world often focused on short-term results. Whether it becomes the main energy source of the future or remains an ambitious vision, the idea encourages humanity to dream bigger and to invest in science and cooperation. When we look up at the moon in the night sky, we may one day see more than a distant light. We may see a partner in our survival and progress. We may see power stations quietly operating on its surface, sending fuel to Earth. We may see a reminder that solutions to our greatest challenges sometimes lie beyond the horizon, waiting for us to reach them. This is the story of helium-3 on the moon, a story still being written, a story of science, ambition, risk, and hope.